Okay, welcome, people of Earth, to Advent of Code Day 14. Um, Guess we should quickly reflect on Day 13. The big lesson there is, the parsing. Just parsing our input is, sometimes. The hardest part of the problem is not really the right description, because the thing about writing all this parsing stuff is um, there's never any question that we'll get there in the end. It's just a matter of how much time we're going to waste kind of flailing around on the parsing. Um, I definitely get very flustered by writing this parsing stuff. And I think part of it is that kind of the only time I do this kind of text processing these days is as part of Advent of Code. So I am the least confident in in this stuff. And I think it's also, you get flustered on easy stuff because there are so many options. Um, there are 20 different ways that I could parse any of these inputs, and I don't have enough experience, or at least experience lately, to have strong feelings about what the right way to do it is. And so I'm just kind of caught between all these different possibilities. Many times when you're like in the flow and really programming, partly it's a symptom of you only knowing one way to do things. And that's not always a sign that you're doing it a very good way, because you're not choosing among the multiple options. You just only have one choice there. Um, Specifically, what can we learn from day 14? Um, we should have just processed this stuff by hand, or at least we should have broken the two kinds of input into two separate files and just read them separately, and then it would have been a 5-minute task as opposed to a 15-minute task. That's very clear. And it's very hard to remember, for a professional programmer, that we're writing programs that will run only once. So if you can do something by hand, it is almost certainly faster to do it by hand than to write code to do it. And in fact, I know that some people who do these things, they actually are just very good with their editor, and they take the input and they re-edit it into something that matches a parser they've already written or something, and that's not a terrible idea. Uh, I'm not really into that. I like the idea of being able to reuse my code a little, even though you know I am adamant that like programming contests are not real engineering, and you shouldn't confuse the two because they're not. Anyway, so also I have written these things so that you can subscript a string by integer position. I tried to write something such that you could also subscript by integer range, but it looks like the Swift developers, the people who do the standard library, have explicitly disallowed that, which makes it, at the very least, complicated to reintroduce by just writing an extension, because it rejected my extension when I tried to do that. So I added a function called slice that I had forgotten about that does that. And if you want to read empty lines, you got to do this empty subset omitting. I think omitting empty subsequences false, which I had forgotten yesterday. Um, and even past the parsing, like I just wasn't really on top of what code structures I wanted to use yesterday, and so the technique that kind of worked for me, if when I finally got down to what's like the crux of the problem, the hard logic that requires thought, and I built outwards from that. And it didn't result in beautiful code, but it did result in code that worked. Anyway, we are about to go for day 14, so let's see what that's all about. when they're adjacent, something should go between them. Interesting. Okay. Okay. 10 steps of insertion. Wait, what is one step? One application or one application of everything? The first step, simultaneous. Okay, so you apply everything. Okay. Get our puzzle input. Now, we are just going to take these so we don't have to ignore the first whatevers. Actually, how do we do that? There we go. Okay. And then lines split on space. This is using my string split function, not Swift's built-in one. Lines, no, what are we doing? We're mapping, right? So every single line we're going to split. We just need to get our syntax right, but let's try and do this correctly. Okay, and then we have substrings, and okay, well, I can't decide what to do next, so when in doubt, just make sure your code runs and does something useful. Yes, we're parsing that correctly. Okay, so this is our starting string. So let's okay. Now, so first pair, second pair, C. Okay. Ooh. So, for pause in. So this is gonna be the second of our pair we're looking to. Okay. Split. Are we gonna do a lookup table? Yes. Let's do a lookup. Var. From string to character or string. Oh. D0 MD0 equals D1. Okay. Oh. My God, I hate this. I hate this about Swift. Yeah, and we got to do it again, don't we? Oh my gosh. It makes it such an inconvenient such an inconvenient language to do string processing in. Yeah, okay. So, we have all this. Let slice from pause minus 1 to pause. Now why is that? Yeah, okay. If let replacement is D pair, then S minus 1. No. Append S minus 1. Append. I think this is the only one we need in the if, but okay. Oh, this should have been come on, hold on. This should have been a very quick first part, and we have just taken forever doing it. So, S equals NS. So let's just run this once and see if it compiles, which it doesn't. S slice from 2. Right, we didn't even send it a real range, did we? We just did that. Cannot find D. It's M, isn't it? Oh, come on. Oh! R equals M of paired. Let's call that a string. Oh, I hate that. Okay. So, is that what we're getting as the length of S? I would have to read more closely, but when have we ever made the mistake of not reading closely enough? That doesn't sound like us. Come on. Okay. What do you get if you take the quantity? Oh, no. It's not the length at all. Most and least common elements in the result. Wow. Okay. That's not at all what I was expecting. So there's probably a built-in way to do this, but I'm gonna have to do this. Equals from character to int. If there's probably a more efficient way to do that as well, but whatever. take the most common, least common element. Freaks. Values. Oh, actually, we have this open here, isn't it? Values. Oh. Values is a collection, yes. So, max. Ooh, bang. See, we're learning because we did this yesterday. Freaks, values, min, bang. Okay, does it compile? Of course it doesn't. Freaks, C. Bang. We just did it. And 2049. Sure, that sounds like a reasonable number. It might not be right, but it's going to take us more than a minute to debug, so, well, let's debug. Okay, so their example is this. Okay. And NNCB. Okay, well, let's go through this and let's say, and S. So, now what happens? It gets extraordinarily long. N. Ooh, okay. So what's going wrong here? Matches. So we only have to see between N and the second N. We didn't do that. We inserted after, didn't we? So that's all a bit. Let's look at this again. Second pair matches inserted between the N and the C. Oh, hang on. So we're inserting things twice, so we actually don't need this until we leave the loop, at which point we say append S. Last? Is that a thing? Let's try that again. Oh, no, that didn't work at all. For... So you always append the previous one, and sometimes you append something in addition. What did we change there? C, B, N, C, N, B, C. Okay, print pair and R. So let's see what's going on here. It's going to get us a lot of... Why is nothing changing? I think this is all wrong. That's what we're doing wrong here. Oh. What? Well, okay. Pause plus one, because I think I've done... See, I don't know my own slice syntax. That's part of the problem. Okay, that's reasonable. We don't need to print all this stuff anymore. Right? Come on. Wow. I am going crazy long. And I think I am right about this. Okay. Okay. NC, NB, CHB. That looks good after step one. Okay. 1588. 1588. Okay. Oh, my God. We're not good programmers because we had to debug. But now we are good programmers because we're going to get the right answer. Oh, but okay. That's fine. 3831 seems reasonable. So a little slow, but we got there. Now, okay. This is going to be way too long. It's going to get crazy slow, isn't it? Crazy slow. So we're just going to have to move to a case of counting the elements or something, aren't we? Because 40 is not going to work. Let's... One of our learnings is that we shouldn't even try this because it's clearly not going to work, and so we shouldn't waste any time doing it. But... Oh, I'm stupid. Because it's going to grow exponentially each time, so clearly this is not going to work. And so I don't know why I'm wasting my time doing it. So, what's our new strategy? Oh, I kind of don't have the energy to think this through tonight. So the most common element, strong enough. So every time we introduce... So when we introduce a new something... Yeah. 11. See, this is stupid. It's never going to get there. Let's do it 10 times. And let me actually print each of these things because I'm curious what the numbers are. Actually, you know what? Let's do this whole thing every time, because we might just see a pattern, and we can just apply the pattern, right? So, 20, what pattern do we see here? 2, 3, 6, 17, 23, 47, 90. It's not quite regular enough for me to know anything, is it? 18. I mean, it's pretty. It's close, you know, because they both double. But that's not going to get us exactly the right answer. let's actually, hang on. Okay. It's always F, right? Yeah, so it's always F is the biggest. So let's write that down. F. And the smallest is always C. Smallest is always C. Let's look at our rules. So, we do have things that introduce C's. Well, we have a lot of rules. So, there's not much we're going to get by analyzing those by hand. We do need a general solution, I think. Why are F's so common? Yeah, I don't think we're going to learn much by looking at it by hand. Okay, so, what are we going to do? Keeping this whole string is not really going to work. So if we have A, B, and then it turns into A, C, B, then we know we're going to get, then what does that change? We're going to no longer do the AP, AB construction, but we will do an AC and a CB construction. But that won't change any of the pairs because we just put C between the other two. So every rule simply cascades to other rules, right? So we can link an AB rule, an AB arrow C rule can be linked to an AC rule and a CB rule, right? And those can be similarly linked to other things. So, if we apply an AB rule, so we just have to do that 40 levels deep for every rule, and then see what rules we apply the first time. I think maybe that logic works. So I don't think I fully followed my own logic there. So what are we saying? So we have this D. No, we have this M. Right? We don't actually want to print anymore. We have this M. And when an M rule is applied, you can't do that, can you? How do you build a string from characters? God, I hate... Swift is just so terrible at this. Well, let's, just for the sake of learning Swift, let's see if you can do that. And then V plus K1. Yeah, okay. And this is actually kind of classic being bad at programming languages, because we're focusing a lot on the programming here and not the algorithm. And that's really how you do badly at this stuff, because what we want to do is spend all our time thinking about this working, not about how to implement it. But anyway, so the next rules, so we know the next two rules that are going to be applied, right? So what is rattling here? I don't like noise from things. This is like our frequencies, so it's going to be from character to int, but some of our characters are strings, so this is horribly embarrassing. So we do that. So we say, we do this thing again. Okay. So let's say we might need to memoize this, and we don't have a decorator for that, but we can implement it by hand. So changes for rule. And then okay, so we're going to hoist this out, and the caller is going to do that. Then we're going to say changes for rule. Now this is just going to grow exponentially, so we can't do that 40 levels deep either. So I think we're going to have to change the calling interface. Am I doing badly at this, or is this a hard problem? I don't know. So let's... Now let's actually return this. Right. So... Come on, what are we doing? But then we need to know how many levels deep we're going. But then at each level... Yeah, so we'll parameterize this by int, and then we will return this. There must be an easier way to do this. This is quite a complicated solution I'm coming up with here. So, okay, for C I in levels -1. No. Okay, so that's how we merge those together. We do that for both of those things. And then we return the changes. I don't know how we're going to debug this because I'm sure we have mistakes in here. And now we actually want to memoize that. So let's varchar and this is and tuples can't be struct cache key is hashable, right? Okay, and then we do what? Then cache key 2. So I can't explain this at the same time I'm I'm typing it. I'm just not good at that. So what we're doing right now is memoizing this function such that if it's called the same parameters multiple times, we won't reevaluate it, and particularly we won't reevaluate the recursion of it if we call it the same parameters multiple times. And this way, there will only be number of levels times number of values times number of keys, which is a manageable number as opposed to the exponential number, which we would do if we did. This is also pretty much dynamic programming as well. Okay, so if it's in the cache, then don't bother doing any of this stuff. But if we did compute all this stuff, then we say cache. Oh, let's hoist this cache key, right? And let's say, cache key equals changes. Okay, so now there's no way this is going to work on the first run. But should we do it anyway? Okay. Okay. 4. Let's see what happens. B 40 or 39. That's part of the problem. Is I don't even know what that is doing. So equals from a string to, what are we doing? String to int. Impact. Okay. Equals. So let's see if this hangs us forever. Well, it didn't hang us forever. Levels. What were the other ones? And that was on 26. Changes V. Yes, because we know. And this is going to be the same thing. No, I'm not good at programming. 29 levels. So I think darn. Oh, darn. Darn. Are we gonna LLDB this, or I mean, what? It's terrible. It's terrible. I don't know how to do this. No. Okay. Oh no, but we have to actually Swift C this, don't we? And then we have to 793 it. Did we blow our stack because we didn't do something right? Why is this such a difficult operation for you to run? Come on. Hello? That's making me angry. Bad access. Get generic meta. I don't. Why is this going so badly? So we can't even... Ooh, what is going on? LLDB is just killing it. I don't understand that at all. Why is LLDB? Now we gotta kill that, don't we? So what is it? Wow. So no help from the debugger there. Let's think through what's happening. In fact, let's actually print this each time. See how far we get just running our thing. Okay. L negative. Oh, because we didn't ground out our recursion. Duh. If and we have a long way. So we got all the way through 1, 2, 3, 4, 5, 6, 7, 8, 9. So what did we do here? I've lost track of what we were doing. First of all, we're only going to do this once now. Rule impact. So this is actually looking like what I was expecting. So modulo off by 1 errors, I think we might have our logic in place. So let's actually go through this. So what are we going to do? Now we want to know, we want to add up all the rule impacts of all the rules that we apply, right? So forget this stuff. Forget this. For every pair, we look that up. We don't need this. Our total impact is a thing from strings to ints. Right. Okay, the dog is bothering me. Go away, dog. I'm busy. I think we might have an answer, sort of. Okay, then what we really want and pair, then for we do this. We didn't really need to do the compute the rule impact table, did we? Maybe it's 39 and not 40. Who knows? R pair. And we got to get our indentation levels right, obviously. And we don't need any of this. And we don't... Do we need any? No, we don't need any of this. So don't need any of that. So what are we doing? Total. Let's just see. And this isn't accounting for what's in the initial changes. Changes. Total impact. We are spending a lot of time doing a lot of programming. And again, not thinking so much about the algorithm and our off by one errors, which is really where our focus should be. But, dog, listen, I know you need to go out, probably, but we gotta finish this in under an hour, baby. So, come on. Okay. Dog, no, go away, Bailey. Bailey, no! Okay. So we did kind of compute a total impact thing here. How many cache keys did we? Oh, of course, because we did a lot at first, and these are just because they were all cached. So we got there. Now. We're going to definitely need to do the test data to debug to get her off by one errors. I'm not even going to try doing it for real. So, the most common element in the is B. At least it doesn't actually tell us the steps along the way. Oh, but if we change it to 10, if we change this to 10, then we could have tried it, because I think it's just our off by one errors are probably the major problem. So, print. Oh God. Total impact. Total impact C plus equals 1. Okay. Print total impact values max. Total impact values min. And then total impact. What am I saying here? Then let's just subtract the 2, right? It's probably faster than typing it all over again. Okay, so no, of course I got something wrong. Oh. I mean, I get that it's philosophically wrong, but Python's like conflation of strings and characters is incredibly convenient. Total impact, yeah. Okay, so 3831 was the right answer the first time. Oh my gosh, we might be almost there. So if we change this 10 to a 40, and then we run it, and it was the third number. I have no idea. Is this it? Yay! We were pretty slow though. So I'm curious. There was probably a much faster way to do this. Well, we didn't do terribly. We didn't do terribly, to be perfectly honest. Let's just briefly walk through what the logic, because I know how terrible a job I did at explaining what I was doing for the second part here. Ignore the whole cache and cache key thing for a moment. The point was, every time we apply a rule, right, we split up the pair, so the rule that we're applying is not going to be applicable anymore. But two additional rules will be applicable. And each of those rules will make two more rules applicable. And so what we want to do is explore that exponentially large tree and figure out what characters are added by that exponentially large set of things. But the problem with that, of course, is that this tree is exponentially large, right? However, each one of the nodes in this tree is actually going to be duplicated many, many times. So if instead of creating new nodes, in this and building a real tree, if we just compute a directed acyclic graph, meaning we reuse that node wherever it's used, then we don't get exponentially many nodes because we just go to the same node and all we have to do is ground out that node once. That's a terrible explanation of dynamic programming, but that's the basic technique. The way you implement that technique is that you say, well, we're only going to evaluate this function once for every set of parameters that we pass it, right? And if you have a child with this set of 3 parameters, then you'll call this function to calculate it. But if it's ever been calculated by someone else who has that child, we'll just get the result from that call. So we won't have to descend down all the way to the bottom of the tree to get it. So that's what these cache keys and this cache is for remembering what the last time we called this was. So it's no longer an exponential number of calls. In the worst case, it's the number of levels times keys times values, which is, there are only like 20 keys and values, so that's like 400, and then there are 40 levels, so there are 16,000 possible calls, which is nothing, right? And this is a technique called memoization. Yeah, and then we know what the total impact of applying any given rule is, and I had actually put them in this thing so that I knew what the cost of applying a rule is. But the great thing about memoization is we can just compute it from scratch here. It doesn't matter. We don't need to cache it because we're already caching it, right? So we just computed anew for every rule that's applied, what characters are added, and we get a big map of, for this character, this is how many times it's added, and then we just have to throw in the initial characters, and then we have the total impact is really misnamed. It's just the total number of characters in the resulting string. So we got to the finish line. That was almost an hour to solve that problem, but that actually felt like an hour-long problem, at least the way I did it. This is one of those things where I would be interested to go and looking at other people's solutions because there might be a much more straightforward way to do this. But anyway, thanks for joining me, and I'll see you here tomorrow for day 15. Bye.